Hey, we're in the last section of the course. What do you think about that? I'm so excited now that we'll finally get this course finished. You're probably as excited as I am, and let's just see what this looks like. This is a section called the two-sample t-test. So, sometimes called the two-independent sample t-test. The section 2 of chapter 11 was the matched pairs t-test. Each of those kinds of tests involve pairs of information, but in the two-sample test, they're not paired up. The samples might be different sizes and they're chosen independently. So here's what it does. It compares the results of samples obtained independently from two populations. So you sample from one population and you sample from another population. So you have two data sets you're looking at. They might be the same size, they might not. The population you're sampling from are assumed to have normal distributions. Of course, the usual large sample condition is a substitute for normal distribution. So what we want is for the sample means to be normally distributed. And for large samples, the sample means are normally distributed even if the population isn't. So we go here, or large samples. Lots of times with these type of tests, you're trying to compare experimental results, and larger experiments cost more money, so you might have smaller samples, so you might have to be more careful of checking that the distributions look approximately normal. But we'll talk more about that later. It uses the sample means and sample standard deviations from each of the samples. So you've got two samples you're worried about. Samples obtained independently from two populations, so two different samples. Use the sample means, sample standard deviations to construct a t-statistic. So we can use the t-tables, or you can use a calculator that understands t to analyze it. There's also an associated confidence interval for the difference of the population means. So we haven't talked exactly how the t-statistic is used, but we'll find out in a minute. Here's what the t looks like if you want to compute it. So it's the sample mean of population 1 and the sample mean from population 2 subtracted, the mean of 1 minus the mean of 2. So lots of times those are null hypothesis means. If you're doing hypothesis testing, you might be assuming the means are equal, in which case mu1 minus mu2 would be 0. So a lot of times that's just 0 up there. And then downstairs is this standard error calculation. It's the estimated standard deviation of this difference. So when you take something and you divide it by its estimated standard deviation and the something is normally distributed, you tend to get a t-statistic. So that works here. Here's the way the estimate works. Sample standard deviation of the first squared over the size of the first sample plus the sample standard deviation of the second squared over the size of the second sample. And then you take the square root. For the confidence interval formula, you take the estimator. So here's the estimator. What are we trying to? We're estimating mu1 minus mu2 is in this interval here. So we take the estimate of mu1 minus mu2, which is x1 bar minus x2 bar estimates mu1 minus mu2. And so that's the estimate. And here's a critical value, and here's an estimated standard deviation. So that's been our way of writing down confidence intervals. Hasn't changed. Estimator plus or minus critical value times estimated standard deviation. If you have the actual standard deviation, this tends to be a z. If you estimate it using the sample, this tends to be a t. All right. The degrees of freedom that you're going to use for t, because I have a t here, it needs degrees of freedom to proceed, can be taken to be the smaller of n1 sample size of the first sample minus 1, or n2 minus 1. And in parentheses there we say this is a conservative approach used if normality might be suspect. So if you're worried about whether or not you've met the conditions explicitly, that things might be a little off, one way to counteract that is to use this estimate for the standard for the degrees of freedom. It makes it harder to reject the null hypothesis, and it makes the confidence interval wider. So we call that a conservative approach. Bigger intervals, So it's less likely that you don't capture the true mean. So that's fair, and it's less likely you're going to reject the null hypothesis. If you use that degrees of freedom, T has to be bigger for you to reject the null hypothesis. The real degrees of freedom comes from a formula which your calculator uses. So there's a formula your calculator uses which tends to be larger than the n1 minus 1 or n2 minus 1. So larger degrees of freedom allows T not to be so large and still reject the null hypothesis. So if you know you've met the conditions, randomly sampling, simple randomly sampling from two populations, I should probably put here obtained using SRS. You can't really degrees of freedom yourself out of a condition of not sampling properly. So if you haven't sampled that represents the populations accurately, there's no fix you can make to your statistics. There's no adjustment you can make. It's just going to be wrong. So you have to make sure the sample at least represents the population effectively before you start even computing anything. So if you were computing, if you get information collected from voluntary response or from some source that doesn't cover the individuals you care about, then the whole thing's going to be suspect and not really work. So be careful. Okay, so we said your calculator is going to use a complicated formula. We'll see that later. Or you could use this if you're just doing it by hand and using the tables. And here we're going to come up with an example. You have an example on your sheet. Our example is a double-blind study. Now, double-blind studies is where the subjects don't know which treatment they're receiving, and the people recording the results also don't know which treatment the subjects got. So it's hard for something to creep into the data collection just unconsciously by thinking that, oh, I know, I've got the real pill and my friend is taking the sugar pill, so I should feel better and they shouldn't feel better, and we all know that, and so that even the researchers know that. And so that sort of clouds the way the information is being collected. And so if you can do it, you'd like to have double-blind studies when you're doing an experiment. Make it double-blind, so the people recording the information and the people who are being subjected to treatments don't know which treatment they got. So they'll open an envelope, take a pill out of it. The envelope's numbered. They'll write the number down. They'll write down their experience, and they'll submit that. And then that'll be tabulated, entered into a computer system. And then the real researchers, once that all is done, they'll run some stat software on that to see what the results were. And that way, you're pretty sure that you haven't entered information in a biased way or excluded something because you thought that can't be happening because that person got the real medication or whatever might be happening. So our example is double-blind, where subjects take a pill randomly assigned as one of two kinds on the onset of a migraine, and they report the number of minutes until the symptoms subside. So there are probably some migraine sufferers out there. It's not a pleasant thing, so if you're a migraine person and you're part of this study, you'd be minding your own business, going about your daily routine, and you feel a migraine coming on. You take the pill, and you see how long it takes before that feeling goes away. And chances are the migraine gets worse before it gets better, and you have to decide when you feel better. So that's the reason for not knowing what pill you took. That might impact the way you report your results. The researcher is interested in finding if the two types of medication have different average times to relief. So maybe one is a lot cheaper than the other, and you want to know, are they about the same? So we could recommend this cheaper treatment. Or maybe we're thinking, we've never compared them side by side, and maybe we think from the experience with our patients that the second treatment seems to be a lot more effective. But I don't know. Maybe it was the first one. And so in those kinds of situations, you're just worried about finding a difference. And so maybe what you saw in the patients wasn't big enough to be statistically significant. There's what they call anecdotal evidence, where you've just seen a small number of patients, and for reasons just due to random variation, you saw a certain pattern of behavior, and you have a feeling that one treatment differs from the other. And now you're going to do a study to see if they're really about the same or not. And we'll be doing that shortly once I put the data up on the screen. And I think I have to go back to my document camera because there's going to be some calculator work here. And that's probably the best way to do it. So this might be my last Learning Glass screen. Yeah, I should not get too excited yet because there might be other corrections that need to be made in some of the recordings I've already made. But I'm getting close to the end, and so are you.